Hi, everyone, and welcome to our webinar today. My name is Paul Bemis, and many of you know me. I'm the president and CEO of Applied Math Modeling. Just a little background on myself. If you don't know who I am the president, of course, and have a background in both mechanical engineering and electrical engineering and business. I kind of grew up building computers. I worked for HP for many years, working on computers, first high performance graphics and then high performance computers, and became a business person ultimately at HP and began working with a variety of software companies, trying to convince them to use, of course, our new hardware that we're building in high performance computing. And through that, I got to know a couple of different companies that I ended up going to work for. One of them was the Ansys Corporation, where I was a senior executive and responsible for their simulation tools, mostly finite element analysis, but also fluid dynamics. And then ultimately, I went to work for a company called Fluent. And Fluent was the market leader, probably still is in terms of a code for computational fluid dynamics, which kind of took me back to the beginning of my mechanical engineering base. While I was there, we started working on tools focused on specific application areas. One of them was data center design. I ultimately purchased from the Ansys Corporation, who then acquired Fluent, a tool called CoolSim, and today we are the developer and full support and sales for CoolSim. That is a tool primarily used for steady state analysis of data center white space. But we also are a partner of Ansys in that we use their technologies in our tools and in our products. And we also have a consulting service that provides services actually far beyond even data centers. We do a variety of work ranging from analysis of clean rooms to analysis of gun ranges, interior gun range designs to hotels. And so we do a lot of external modeling as well. And not all of this is exposed in CoolSim. And so today what we're going to be reviewing is a few of these case studies we've done on external flows. This is still in the data center space. Specifically, we're talking about data center design here, but we're talking about external flows over the building, generally related to dissipation of heat. And problems that occur when you have certain situations like wind. Now, a little bit of bookkeeping here. If you have questions as we go through them, I have two displays lit today, and I have on one display all of the questions that you might ask. It's empty at the moment. You haven't asked any. But if you do want to ask a question, go ahead and type it into the chat box. There should be a question box over there on your right with your GoToMeeting panel or your GoToWebinar panel. Go ahead and type in the question, and I have with me one of my technical lead, a person who is in my consulting group. His name is Abhishek Jean, and if I can't answer the question, I'm going to pass it over to Abhishek, and he's going to answer it because he's the person who is in charge of the development team or the engineering team that does a lot of this work. I am pretty good at it. I'm a generalist, however, and Abhishek can provide detail if you want it in areas that I might not be able to answer. So that's how we roll, and we tried to make this 1 hour. So we try to go for 45 minutes, and then we try to have question and answers at the end. I will have contact information at the end for any of you who want to reach out to us, and we'll go ahead and get rolling. So let me start off with the first topic here. What we're talking about here is heat dissipation in the data center. And just to review, and I apologize for some of you who already know all of this, but the way that it works in a data center is we absorb the heat in the room and dump it to the atmosphere. It's that simple. Get it out of the room and into the atmosphere. But this gets complicated because you have issues of short cycling. Short cycling is when the fluid, the air, tends to spin around the heat exchanger and doesn't go through any media. It doesn't go through the atmosphere on the outside, doesn't go through the equipment on the inside. So that's a problem we're going to be talking about today. Now, CoolSim is primarily focused on inside the data center and trying to dump the heat through the air handlers or craws or cracks or crays, whatever you want to call them, in the room. They're fundamentally heat exchangers. You're trying to get hot air back to them and you're trying to get cold air out of them. And that's primarily Coulson's job. Inside, we work in the white space, but the same physics is available and applicable on the outside. So outside, you're trying to do the same thing. And oftentimes there is recirculation that happens in the what they call dry coolers or cooling towers or whatever it is they're trying to use to dump the heat to the outside atmosphere. This causes efficiency of the data center to drop substantially. It is particularly of importance under failure mode conditions because in failure mode conditions, you often have an atmospheric condition going on, like, like a lot of wind or rain or something. And it is those conditions you want to consider during the upfront design process. Now, I'm going to use this slide here. I'm going to walk you through it a little bit. This is, again, review. I understand, and many of you know this, but for those of you who don't, I'm just going to describe how this system generally works. And here I've got essentially the Rankine cycle shown. And let me just go through it. What we do in data centers and so forth, even air conditioners, your home, I'm going to start here with the compressor. So here's the compressor here, and we're squishing a medium gas. Of course, the ideal gas law says that if you squish the gas, it gets hot. Once the gas is hot, it goes up into the condenser and gets dumped to the atmosphere through a heat transfer process. Now, in a DX system, this heat transfer, which is also over here on the Rankine cycle happening right here. So here's the work going in, and it's raising the temperature until that medium gets to a very high pressure point and becomes liquefied. And then we go through here to heat dump stage. This heat dump stage is to the atmosphere. It's always to the atmosphere unless you're lucky enough to have an aquifer, which I actually do have a customer with an aquifer underneath them. So it does sometimes goes other places than the atmosphere, but generally speaking, it goes to the atmosphere. Doesn't matter if it's a DX system, a direct expansion system, or it's a chiller. The only difference between those two is in a chiller, there's a water loop out here that dumps the water through a cooling tower or whatever to the outside. And over here, there's usually another water loop that's picking it up inside of the data center and bringing it into the evaporator. Fundamentally, this cycle is the same. It's just in a chiller. This is constrained within the chiller itself, this loop, and when a direct expansion system, this is exposed directly to the room. It's the only difference between them. Everything else is fundamentally the same. Once you get to the point where the air, or the medium has cooled it enough, then you drop to a expansion cycle. You go through an expansion valve, and that drops the temperature down because, again, PV is RT. Ideal gas law says that if you drop the pressure, temperature is going to drop with it. This chart, this is an ideal state here. There is some entropy growth, so it's not ideal. This number 4 and 4 prime, the difference between those two is entropy growth caused by inefficiency of that process. It's not perfect. And then you absorb heat. So this is the absorption over here. This is taking place in the room. You're absorbing heat into, if it's a chilled water system, into what's called a CRAH, computer room air handler often. Sometimes it's called a CRAC as well, computer room air conditioner. And then we go through the loop again. Now, the governing equation also for heat transfer, and if you take anything away from this webinar, try to remember this equation. It helps you a lot. Heat transfer is equal to the flow rate, the mass flow rate, that's this flow rate, the flow rate across these heat exchangers, both of them, times the density of air, which is fairly constant, times the specific heat of air, times the delta T. So now this delta T is very important. So these units right here remain relatively constant. So it becomes a trade-off between heat transfer, flow rate, and delta T. Now, I've got here R&S, supply and return. I pulled this out of one of my training slides. That's talking about inside the data center, but it's also the same exact equation out here in the atmosphere. It is the supply return, sometimes called the suction side and the dissipation side, but it's essentially the delta T across this heat exchanger. And if this heat exchanger starts to recirculate on itself, that spells trouble because the outside atmosphere is one of these T's, and you're stuck with it. It's not going to change. So if your intake temperature isn't low, then you're going to have poor performance and your ability to dump heat is going to decline, and that leads to cooling problems. So I wanted to just put this up and remind you that this is what we're talking about. I wanted to remind you of this equation because if you can kind of keep this thing in your head, it helps a lot. Essentially, what we're talking about here is heat transfer is correlated very highly to, almost linearly, to mass flow rate and delta T. Okay, you've got to have one or the other or both in order for you to get good heat transfer. So now let's just go to outside units. Inside the data center, we have pretty good control. You know, I mean, it's not perfect, but at least we have control over it. We can adjust the amount of air coming out of those air handlers. We can work on air management techniques such as hot aisle, cold aisle containment, and we all have experience doing that, most of us. Outdoor gets a little trickier. We've got outdoor wind, we've got wind speed, we've got all kinds of problems going on outside that are beyond our capability to control very well. Time of year, and we also have a space problem. It's a growing space problem. The heat exchangers outside are getting closer and closer together as we try to dump more and more heat from these data centers. And this causes problems. They tend to bleed into each other. We run into situations where wakes can occur, and we've seen, with a hot roof. So outside's becoming more of an issue. And that's a lot of what we're going to be talking about today. Now, the other thing about outdoor units and cooling systems in general is they're specified at ideal conditions. Generally speaking, when you buy a piece of equipment like a cooling unit, they'll say to you, if you're in the United States, they do it in tons. If you do in Europe, it's kilowatts. But this unit is capable of a certain amount of capacity. Sometimes they use BTUs, not very much anymore, but mostly it's kilowatts or tons. But as the inlet temperature rises, that capacity drops off, and it drops off non-linearly. I've had many customers say to me, well, I can't keep my data center cool, and I don't know why on a hot day. It's unusual because I certainly have enough capacity because I bought this many tons of cooling. Well, guess what? It's not a constant. The tons of cooling, or BTUs, or kilowatts, however you want to measure it, actually declines as inlet temperatures go up, and it does it in a nonlinear fashion. And if there's any recirculation going on where it's coming out the hot side and going back into the cold side in a loop, short circuiting, then this makes it even worse. It's best, therefore, to address all of this at the design stage. Get it all done early, get it all out ahead of time, and try to deal with it before you run into problems in the field. And if you're in the design business, you're going to want to look at that. And CFD is an excellent tool to figure out how to solve those things early, because you can't test it, you haven't built it yet. And furthermore, with CFD, you can do what if conditions. What if the wind's blowing from this condition? What if it's blowing from this direction? What if it's this temperature? What if it's this velocity? You can do a lot of what ifs that you could not do in the real world. It's not practical to try to do them in the real world. And even in CFD, it's not necessarily practical to do them for all combinations because it takes time. But you can study worst case conditions pretty easily, and you can do what ifs under those conditions. So you can put in obstructions to wind, you can put in, what if you lose capacity? To set these up correctly, you need to have the discharge temperatures and the inlet temperatures on the heat exchanger. HX, by the way, is an acronym for heat exchanger. So these devices are very sensitive to the difference between inlet outlet temp. That's how they work. You also have to take into effect buoyancy. Buoyancy is an important element to take into account. Buoyancy is essentially, hot air rising due to change in density. That will cause its own stack effect where you'll have thermal conditions and velocities that will occur based on change in temperature alone. Much the way a hot air balloon floats is that same kind of idea. And we also need to be careful of boundary layers. They can be very important, particularly in cases like surfaces of rooms. A boundary layer is the layer of fluid, in this case air, very close to the surface of certain components. Very important in many designs, wing design, aircraft design, but also important in here because the temperatures near the surface of these roofs in particular can be extremely high. And then, of course, meshing. Now, this is a CFD specific issue. Refining the mesh and picking the right turbulence model to be able to predict these wakes effectively is a skill. It is something that comes with experience. We represent at Applied Math Modeling, lots of experience in CFD modeling. And Abhishek's here to represent much more experience and expertise than I have, and I've been doing it a very long time. So we're going to discuss these in case studies over the next 30 minutes. If you have questions or something doesn't seem to make sense to you, please type your question into the chat box or put your little hand up or something. We'll try to address it. So let's get into the first one. This is a chiller yard. That's what it's referred to. Chiller yard is just a place with a bunch of heat exchangers. You see them here in this image. You also see diesel generators next to it. And over here, of course, you see a solid fence. Now, this happens a lot where you're trying to make the facility aesthetically pleasing. So the way that is often done is let's hide it. Now, you're also from a design point of view trying to keep these devices as close to the stuff inside the data center, which is in this gray box, as you possibly can. Because, these are generally piping and distribution costs money. So the shorter that distance, the better off you are. And if you can put these all in one location and stack them up, that'd be great. But the problem is when you start to stack them like that, they can run into problems. So the issue you have to worry about here is under wind conditions, will one of the hot air exits start to infiltrate into the adjacent device. So in this particular case, this came from a real study that we did with an unnamed customer. And we model it as per the dimensions for every chiller that has an inlet or a suction and a discharge. We use a pair. It's called a inlet outlet pair or a boundary layer pair, not a boundary layer pair, but an inlet outlet pair in Fluent. And we use those a lot. So we pair them on inlet outlet. We set the sizes according to the size of the fans. We set the boundary conditions for them, do all the geometry exactly the way it is. In this case, we're modeling the generators as blocks because they're not on in this case. We're just studying the effect of atmospheric condition on these condensers. The mesh is important. We need to get a good mesh here. And Abhishek, maybe you can give us a little bit of detail on the mesh. This is obviously a tetrahedral mesh that we're using here. And you can see in the image, as it gets closer to these devices, mesh density goes up. Do you want to give us a little bit of commentary about the importance of meshing and how it's done or was done in this case?
Thank you, Paul. So what happens in this mesh is we need to have a denser mesh or more mesh near the exit in the chillers where the air is coming. But very far off from those chillers, we do not need a very big mesh because the gradients of flow or temperature are not very high there. Now, some people also wish to use a very fine mesh, but that would only be causing more computational time and not a very significant increase in accuracy. We used approximately 2 million meshes here, and that we found was good enough to simulate what we wanted as a result.
Mm-hmm. Now, how do you know when a certain density is enough? What is the criteria that allows you to understand how dense to make it near the inlets and outlets, Abhishek?
Okay. So if we are doing a new problem, then what we would like to do is we make a very coarse mesh, make it finer, see the result, make it even finer and see the result. And if the last two results are within a percentage of each other, we say that the second last mesh was a good mesh. That's a grid independent study that we do. But in most of the cases, after a reasonable amount of experience in projects, you tend to understand where you want what kind of mesh.
Yep. So experience helps a lot, but what you're looking there for is numerical differences based on density. And once the numerical difference of the solution begins to flatten out and not change much, you feel you've achieved the level of density of the mesh high enough to be able to capture the physics, correct?
Yes, please.
Now,
That is a scientific way of doing it.
Yeah.
But experience also counts, yes.
Now, the other thing here I wanted to point out is the mesh we're using here in this case is we get to use the ANSYS tool set, which is a real benefit of being a partner of ANSYS. And what we've used here is tetrahedras to model this. Tetrahedras are 10-sided polygonal representations. You see them here. For those of you who don't know CFD, just a little bit about it. You can imagine these are polygons in space. The non-solid is where we're interested. We're interested in a non-solid area or volume. And we fill it with these tightly packed representations. And on each of the surfaces of these structures, which are 10-sided polygons, effectively, we solve the equations of physics, which are conservation of mass, conservation of energy, and of course, conservation. What did I forget, Abhishek? Mass, momentum. I forgot momentum. So mass,
Yes.
momentum, and energy, the three. And we do it for every one of them in the mesh. And he talked about 2 million in this case. You can imagine having 2 million elements and you're solving for all three of those. Those are nonlinear differential equations for each one of them. And that takes a lot of computation and a lot of time. So you want to try to keep that as low as you possibly can. In other words, over meshing it isn't what you want to do because it costs time and doesn't give you any better fidelity. You want the right mesh on the right stuff at the right time. Here are some of the output that we get out of these kind of runs. These are what we call path lines. Path lines are simulated particles in space. So we're just simulating the path. In CFD, you can artificially put these in, and you can put in, and we call them seed points. The number of seed points here, I think, looks like we have 1 seed point per output, maybe 2. And what you can do is track them through air. Because we have modeled every single polygon that represents the air, we can actually see what's going on. And this is the power of computational fluid dynamics. It gives you the visual ability to look at the airflow and understand what's happening. It makes the invisible visible. And this is very important when you're trying to understand it. And you can see already under a wind condition here that we've got some recirculation going on. It's dropping down, and it's going to drop down, and it's going to be pulled into those inlets. You want it to go straight up in the air and go away. But because we have this blunt body over here called a wall, as that air comes over that wall, it's going to start to create a low pressure area and start to cause issues. Now, this is shown here as well. This is in a vector plot. So same exact situation. We're just looking at it from a side view. And you can see the recirculation coming down and getting sucked into the intakes. So we've got issues already with these things being so close together that the outlet is being sucked into the inlet, and it's being caused by this wind condition. So as you know, old Bernoulli said to us that density times cross-sectional area times velocity is a constant. And so what happens is as the velocity rises, the pressure is going to drop. And when the pressure drops, you're going to get a pull, and it's going to go down, and this is going to recirculate. So that's what's happening, and that's what's causing that effect to occur. The result is shown here in temperature, because we can see some hot spots that's already occurring, getting very, very high. It's actually where you would expect it to be, right in the center of all of these things, where they're recirculating all of these conditions. So a question did come in here that I'd like to address. The question is that considering experience, what parameters, such as external temperature, wind, speed, would occur simultaneously? In other words, how do you anticipate the worst condition that you might anticipate or try to set in there? And the answer to that is we don't always know. But what you can do in CFD, the beautiful thing about this thing is a model. It's a math model, and you can experiment with it fairly easily and test different parameters. For example, is wind the most important parameter we're facing here? Or is external temperature the most important parameter? And by wiggling one and holding everything else constant, you can understand the sensitivity of the design to that particular parameter. In design, it's called sensitivity analysis, and it's done with a variety of methods. But one method is just try it and see how it affects it in your model. And so testing different parameters is a way to know it. The other thing we tend to do is look at the geography that we're operating in and understand what the weather conditions are in that geography. You know, in this particular case, it was a prevailing wind from one direction they were worried about because that area is known, that region of the earth is known for prevailing wind from the south at 20 miles an hour. I mean, I'm not sure exactly that's what we did in this case, but that's not unusual, that you'll have a prevailing wind that tends to cause issues and or is prevalent, and they'll want to see that. So then what you can do with CFD is analytically get data out. It's not just pretty pictures, but you can analytically do post-processing on these surfaces and figure out for every one of them what the average temperatures are. You can look at the gradients across them. Gradient, again, being change in temperature as a function of position, and calculate very accurately with high fidelity what the temperatures are going to be for each one of those things. So inlet outlet temps. You can see here the ones in red are the ones we're most worried about because there are specifications on these devices and they're only supposed to get so hot. So it can be used for things like derating. Well, look, I've got 187, I've got 205 coming in on the intake of this one. I've got a discharge temperature of 235. How does that unit perform based on that temperature delta, and what's it going to do to the room? So when we do calculations such as energy calculations or performance calculations, you can derate. Back to my point earlier about the manufacturer giving you the best numbers they have. When a manufacturer hands you a cut sheet, they're selling you the best numbers they can possibly come up with. You know, this car gets 45 miles to a gallon. All right, well, when? Well, when going downhill with a stiff tailwind. You know, I mean, I'm kidding a little, but they try to make sure they put their best foot forward. That's called marketing, right? Now, what you're trying to figure out in your design analysis is, well, what happens if I'm not going downhill with a 40-mile-an-hour tailwind? What if I'm going uphill and it's steep and it's a hot day and I've got wind against me? How's it going to perform? And that's what you can use this analysis for. And you can derate them. The performance and behavior of a heat exchanger is fairly well understood. So having a curve that represents the basic behavior is something you can get your hands on, and we have the ability to derate these things and understand what the real cooling capacity of these is under those conditions. All right, let me go to another one. This one is one that many of you will be familiar with. This is this is what we're faced with in today's environment. Here it is. It is the top of a building that is just jam-packed with stuff. Now, not all that stuff is yours. You know, if you're out there doing design, you know that that roof is being shared by a lot of different vendors, a lot of different people, a lot of different stuff going on. You see generators here. These are auxiliary generators that are being used in the case of a power failure. Cooling towers over here that are being used to dump heat. And these are what we call dry coolers. Dry coolers are, you know, typically a chiller with a dry cooler that's dumping heat to the atmosphere. So very, very crowded rooftop. The way we model these is, again, we build 3D geometry based on a couple different things. We take typically CAD drawings if we can get them, and we typically can get them nowadays. So we take a CAD drawing, often 2D, sometimes 3D. We take a CAD drawing. We often take a visual. I mean, Google Maps and Google Earth are wonderful tools for understanding exactly what's going on, and you can move around and take a look if it's a real site. If it already exists, this is a great way to do it. And then we build a 3D geometry out of that. And then, of course, we build the dry cooler. This is, again, a recirculating pair. So we have an inlet outlet for these. We build these dry coolers to be exactly the same geometry as the manufacturer specifies from their drawings, and we set them up off the ground using their normal setup. We also do detail, like in this particular design, there's a lot of piping going in there. Well, guess what? That's going to affect, you can see right there, the percent area open for those inlets is being constrained by the geometry. There's not a lot of holes over there. It can pull from this side, but it can't pull from over on this side. So we try to represent the geometry as best we possibly can. That does drive mesh count up, but nonetheless, we do it, and because things are getting easier to use, computers are getting faster, and the ability for us to add the specific geometry detail is now much higher than it once was. The result is you end up with a model, a 3D model, that you can then use to play what-if games on. Same thing as before, you assume some boundary conditions. You say, okay, the outside air is worst case 90 degrees. That's at least where we started with this one. We had atmospheric pressure. We had no wind in this case. You start off with no wind and see if you can get that one to work. And this one in this case, we were worried about recirculation itself. We thought the air was coming out of the dry cooler and being sucked back into the intake. So that was the primary reason for doing this study. We assumed roof temperature here of 120, which ended up being, you'll see, too low. We assumed everything else was adiabatic, not transferring heat. And then we used flow rates that came from the manufacturer. So these are the various flow rates and the heat capacity, baseline heat capacity, cooling capacity for these dry coolers and the associated flow rates. And you use those as boundary conditions in your initial run. And guess what? You run into a situation where you begin to see temperatures exceeding, on the inlet side, exceeding specification, which I think in this case was 91 degrees, I think was the inlet temperature. You can also analytically see, yeah, it was 91, you see right there. You can also analytically see how much of the area of that dry cooler is actually subject to that temperature. Because again, it's a gradient, it's not uniform. The temperature is going to vary across the surface of the intake, and so you want to take a look at that gradient. And you can see here the max temperatures, the area that's above 91 degrees can be analytically calculated, and you can get very fine on determining exactly what that is. Now again, path lines, we're looking at discharge, and in this case, we're looking to see under no wind conditions if these are recirculating without any chimneys, without any stacks. You see, it does have a perimeter around the outside of it. It does have a box around the outside, so that's helpful. But they also on these units will sometimes put chimneys that go straight up to try to get it up and out. And you can see here that on this particular one, which is one that's operating at 17.4 K CFM, cubic feet per minute, there aren't any recirculation issues to worry about. And here are the other ones. These are higher flow rate, 34,800 CFM. They don't look like they're recirculating either. So the first question was, are they recirculating? Answer, no. But we started to look at temperature. This is again velocity. Velocity showing us that for the most part, these things are going straight up into the air. Not too bad. Fairly good velocities, certainly coming out of the higher one. Even the smaller one doesn't look like they're recirculating too badly. Velocities underneath are being caused by air being pulled in from the sides. But when you start to look at temperature, you see some elevations going on right here. This made us a little nervous. Why are we seeing elevated temperatures right there? So that led us to, all right, well, let's take a closer look at temp. So you can zoom in on that and turn your density up on your mesh, build a boundary layer, a lot more cells here, and look at the temperature gradient on the surface. How hot is it? We were assuming the surface was 120. As it turns out, we did some measurements on that roof and found out that this was an existing case, that the temperatures weren't 120, temperatures were 150. So they were higher than we assumed, and that was going to cause even more problems. So you take some field measurements to validate your model, find out what's going on, you go back and you rerun it. So in this case, we started running with roof surface temperature of 150 degrees, ambient air of 100 degrees, because that's what it was the day it was measured. And we start to do a similar run, same sort of situation, but under more extreme conditions. And guess what? Things get worse. So now your max temperatures are even higher. Remember, you wanted those temperatures to be 91 on inlet side. They're above that. Max temperature 105 is in red, so I guess they went up to 105. And the ones in red are exceeding the 105 temperature. We got one as high as 110. The area that's being exposed to that is much higher. 78, 84% of the area, cross-sectional area, is being subjected to that high temperature. And as a result, the performance of those machines is going to drop off precipitously. So here we're taking a look at temperature. Again, it's problematic. There's way too much temp underneath these. If you take a close look at the boundary layer, we're seeing that the boundary layer at 150 is moving up into the edge of that inlet, and that's not a good thing. So The inlet temperatures are going up due to thermal contamination from the roof. It is not recirculation. What we determined was they aren't recirculating on themselves. The case is it's just a really hot roof. Now, roofs in this case were black. It was a black roof, and a lot of them are. And you've got solar loading that's causing this effect as well. The result is the cooler capacity, the dry cooler capacity drops off rather quickly. Now, this is a plot. I hope you can see it. It's not great text, but it shows you the relationship of how that performs. It looks like a straight line, but it's not quite a straight line. It's actually the scale on this thing is a little bit deceiving. It is a nonlinear relationship. We plotted it and curve fit it, and we found that it's a second order relationship, that the performance of these things was dropping off in a second order rate. So the point here is your cooling performance drops like a rock when the inlet temperatures get too high. And a couple of degrees makes a big difference. We got this directly from support from the Liebert team in this case, which is now Vertiv. But generally, these people will help you understand the behavior of their devices under change, under what we call off center, off design center kinds of loads, or off capacity kinds of loads. So one of the things we thought here is, well, what if we jack them up? What if we get them up to 5 feet, put 5 feet underneath them? Will it improve the cooling? And if so, how much? This is exactly what you can do with CFD. It allows you to play these what if games. What if we jack it up? How does it affect it under the same assumptions? Very hard to do in the real world, by the way. It's hard to hold parameters constant. Nothing stays constant in the real world, but here you're able to do that. You're able to say, all right, I'm going to hold everything constant. Let's just take a look at height and see what it does to temperature. Also, what effect does prevailing wind have on it? Does a strong crosswind create reentrainment? Do we need chimneys? Would the chimneys be useful? And again, in this case, back to the earlier question that came in, the wind direction in this particular geography was from the south or from the east. So you model it. That's all. You put those new boundary conditions in. Remodeling or reanalysis is fairly straightforward. It does take time. It takes wall clock time, but the model has already been set up. The mesh is set up. The boundary conditions are set up. Just change the parameters and rerun it. Look at the new output. And what we found in this case is things improved quite a bit. That the inlet temperatures dropped. Remember, 105 is the number we were looking for. Now we've only got 2 of them that are in that position. Things improved quite a bit. And what we found in this case was that it didn't necessarily need the chimneys, but the chimneys helped a little bit. So if you had the freedom to add chimneys to it, it would help. So here's a result comparison of the 3, the baseline. Then in this case, we just raised it up in the air, which gave us the biggest bang for the buck. And then we also added scoops to it, put the chimneys on it, easy enough to do in CAD, and put it into the modeler so that you're able to simulate that condition fairly straightforward. And the conclusion was that the chimneys did help. So there's the baseline, there's the variation in the center with the dry cooler and the scoop, and then there's one over here without the scoop. Easy enough to do. And then you can plot them. You know, how do they look? Well, here's the base case up here. That one's not doing too well at all. And these are the dry coolers. There were 11 of them in this case. And then we have the variation right here with, this is the best case scenario here with the scoops and the height. And then the third one, of course, is without the scoops. And you can do more of that. So you can plot them. You can, we have the analytics. The post-processing on these runs allows you to get a very fine detail on the analytics and show you temperatures, very, very finely controlled temperature gradients. So in this case, we found that the most important thing was getting those dry coolers up in the air, and the temperature coverage was quite high. So getting them up in the air made things better. There wasn't any reentrainment. We kind of ruled that out fairly quickly, but we did notice the scoops help because you've got buoyancy, you've got velocity. When you have a temperature delta like that, the stack effect can be positive in your favor, and that's what we found in this case. Okay, so here's another one. This is, we'll get away from dry coolers for a moment and let's start talking about generators, because we run into this a lot too. Um, outside auxiliary generators being used in case of power failure. And oftentimes people don't want to see the generator because it's kind of big and it makes a lot of noise. So let's put something around it so that we can't see it, because that's not great to look at. And let's also try to keep it quiet. So in this case, we have generators sitting down inside a fairly low spot off to the side of the building. And furthermore, the discharge of these radiators, there's two places that generators will discharge. One of them is the exhaust. A lot of people worry about the exhaust itself, you know, the exhaust coming straight up and out. But to be honest, the exhaust is coming out at a pretty good flow rate. So the velocity is quite high. The temperature is high, but the velocity is quite high. And when you have high velocity, you can generally get that stuff out of there. The radiator discharge, however, is operating at a lower velocity, which means it's subjective, it's subjected and sensitive to wind condition. And furthermore, it's a very, very high volume. So it's something to consider. Now, in this case, we have intakes on both ends. We have exhaust coming out right here. And that's trying to get the intakes as far away from each other as possible. That's not an unusual design. But the generators are tight. They're within a foot of each other. And there's this wall. And we're worried about wind from the south predominantly. Now, again, the southerly wind direction, in this case, we tested multiple wind directions. I think we tested primarily 4, north, south, east, west. Found this one was most sensitive. That also matched our logic, our sort of common sense of the design, and that ended up being the one to be most concerned about. The first question becomes, does the exhaust have any effect? The engine exhaust itself have any effect on the overall design? Answer, no. That the engine exhaust has enough momentum to get it out of there. It's not really a problem. It comes up and out under most all conditions. So engine exhaust, not a primary issue. However, radiator exhaust, big problem. First of all, it doesn't come out with a much velocity because it has a bigger cross-sectional area. Although the CFM is high, the cross-sectional area of the heat exchanger is also high. So the velocity itself is fairly modest. When you have low velocity like that and you have wind, the opportunity for recirculation can occur. And that's what was occurring in this case. So if you plot the temperatures on the intake of the heat exchangers, they look like this. You can quantify the magnitude and temperature at the inlet or the suction plane, and you can quantify the impact of recirculation. And here we're seeing that inlet temperature raises up to about 130, 140 degrees. This is due to the mixing of outlet and inlet temps. This causes the generator to work harder. It causes its performance to decline and may cause it to fail, because once its oil temperature gets to a certain point, it's going to start to boil. That's not a good thing. Your machine's going to fail, and that's a problem. So managing these airflow conditions for outside units is important. It's important for both generators and for heat exchangers. They're very high capital cost devices, so you need to really take this into account during the early designs. And taking a look at off-design performance can be very important to help you estimate how to derate these things in cases of critical scenarios. Remember that the reason the generator's out there is for critical scenarios. So understanding its performance under a high flow condition, like a hurricane or a high wind condition or whatever, is important to understand how it's going to behave in the case that you're most interested in, which is the failure case. So designers need to take a look at this, understand it. CFD is an excellent tool for doing this. We have a lot of experience doing this kind of work. It's sort of what we do, nuts and bolts for us. Don't be afraid to ask. So let me just summarize and I'll open it up for questions now. I mean, we got through that material in pretty good shape. I'm at 1244 is what I'm showing, Abhishek. That's pretty good. We did pretty well. I hope you understood it. We are Applied Math Modeling. We're responsible for development sales of the CoolSim data center tool, but we also use the base technologies that sit behind CoolSim, which is the ANSYS Fluent set, to do a lot of other things. We do all kinds of flow conditions and heat exchangers and generators and so forth. We also get involved with clean rooms and things like that. So don't be afraid to reach out to us if you have any issues along these lines. I have a couple of contact notes here that you want to reach me. I'm paul.bemis@coolsimsoftware.com. You can also use info@. We're a good team. We have a lot of experience. And I've got a question. Can you model vapor plumes coming off of cooling towers? Well, the answer pretty much, Abhishek, I think is we can model just about anything you want, right? I mean, do you want to take the question about vapor plumes off of cooling towers?
So vapor plumes can be modeled. The only thing that we would need as an input is what is the size of vapor particles in the uh, plume that is coming out from the cooling towers. That's the only thing. Or if we do not have that, if we do not have the size of those water droplets, then we can assume a bell curve and then do the simulation.
A bell curve, yeah. Yeah, so you would assume a distribution, some sort of distribution based on some kind of, because it's probably higher in the middle and lower on the edges, so you're assuming a bell curve of distribution of vapor, right? As a boundary
Yes,
condition.
please.
Yep. Does ANSYS have a viewer? Yeah, it sure does. I mean, with the viewer, the 3D model viewer that we provide at CoolSim does come from ANSYS. I mean, the great thing about being a partner with ANSYS is I get to use all their tools and supply them to my customers through CoolSim. So the answer is yes, there is a viewer. We have a 3D viewer for viewing all kinds of results in 3D. I didn't show you any 3D views today. I showed you mostly images, 2D views. But yes, the same viewer that you get when you run a CoolSim job and you're able to export the report and view everything in 3D is actually an ANSYS viewer that we provide to our customers as well. So in the case of the first example, the equipment yard, what is a typical turnaround time for these kinds of results? That's a good one for you, Abhishek. You did that work, I think, on that first one. Turnaround time, it seems like we're cranking these things out fairly quickly. Does depend on the complexity, but what was the turnaround time on that first model we did? And the question here, I think, has to do with both turnaround time for the simulation itself as well as turnaround time for the consulting job. So let's do the simulation first. I think that one you talked about having a couple million cells, and yeah, we did a mesh around those cooling towers. What was the turnaround time for that? Do you remember?
Okay. So if we only do a simulation, it would be 8 hours. But the pre-modeling would require at least 7 to 8 days, depending on the complexity of the model one. And second, sometimes the data that comes from the person who wishes to do the simulation is not very good. So we need to create that data that may add to some 8 to 16 hours of effort more.
Yeah. Just to answer your question, or more broadly, we spend an awful lot of time trying to get the data. What does the exact geometry look like? We kid about this all the time. We spend more time trying to get the data than we do analyzing the data. So if you'd like to work with us, one of the best ways to help us is get us the information we need. And what we're looking for is boundary conditions, mostly. So what is the incoming temperature? What is the atmospheric temperature? What kind of wind condition are you looking for? How are these things geometrically stacked together? What are their dimensions? What are their sizes? In 3D, we need all of it in 3D. It's not good enough to give us just a 2D CAD drawing. In terms of turnaround times for consulting jobs, it seems to me that we're averaging about a week or two. Gets a little longer than that in some cases, but Abhishek, correct me if I'm wrong, but it seems like we're banging these things out fairly quickly these days. Is that a fair estimate?
That's right. 1 week is a good time if the input is understandable by both of us.
The other thing I'll point out is we try to be reasonable about this in terms of cost and pricing. This is something we do as a service. It's not our primary business. We're a software sales and development organization, but the CoolSim tool is made to be easy to use, easy to learn, and fast. It's a very highly automated tool. We built it that way. Most of the users of CoolSim are not heads down, 9 to 5, 5-day-a-week kind of users. They're what we call occasional, or sometimes a better definition is periodic users. They use it periodically. This means every time they come into the tool, they need to come up a learning curve and remember how to use it. Or oftentimes it's a new user who works for the same company, but hasn't used the tool before. Therefore, we try to keep CoolSim nice and simple, very simple, so it can be easily understood. There's not a lot of icons across the top. We do that very, very intentionally. So what we put in CoolSim are things that can be highly automated, easily automated. We have automatic output reports. We do automatic parameter variation. We do automatic meshing, automatic solving. That doesn't lend itself very well to some of these cases that we reviewed today because these are all unique cases. The geometry is unique. The boundary conditions are often unique. The case is unique, particularly also as you get into transient, which is one that we'll review in the next webinar. We'll talk about transient analysis because that one can be tricky too. Now, as these things become more, let's say, well understood or more easily automated, or we figure out the patterns that continue to occur, the opportunity for automation does exist, and we'll continue to expose it. The point here is we can model most anything. We can model even phase change, combustion, humidity. You know, Fluent is an all singing, all dancing kind of tool, but setting it up and running it takes a little bit of expertise. So we have that expertise, and because we're a Fluent partner, we have access to all these codes. It is what runs behind CoolSim. So we're able to use them to your advantage through services. We think services make the best sense for a lot of this stuff that's not, quote, vanilla in the sense of being something you run into every day. So, you know, don't be afraid to reach out, and the answer to most any question you're going to ask us is, yeah, we can model it. It's just a question of getting it set up and figuring it out. Remember, Fluent's been around for 20, 25, 30 years now. It's been used to model a lot of different stuff with a very, very high fidelity. All right, I don't think there's any other questions here that I'm running into. One, vapor plumes, we talked about viewer. So I think I've answered most of them. If any of you have another question, please type it in. Otherwise, I want to thank Abhishek for joining us today, Abhishek for representing our consulting team, and I'd like to thank those of you who attended. And this has been recorded, so we will be posting this webinar on our website along with all the others. The list is getting pretty long. If you'd like to have a look at the different webinars we've done in the past, they are recorded, they are there, and it's under the coolsimsoftware.com website. I want to thank everyone for coming, and have a nice day.